Hi, and now we would like to continue the video on differential then. Okay, so let y equal to f of x represent a uh, differentiable differentiable functions. The differential of x denoted by dx is any non-zero real numbers, and differential of y is given by dy. And then in this case, dy equal to f prime of x dx then. Since dx could not have any non-zero values, we choose dx to be small, and we denote this choice by dx equal to delta x. Okay, and the use of differential is to approximate the change in f of x that corresponding to the change in x, as shown in the frame figures. Okay, we denote that delta y is the actual change from f of x plus delta x minus f of x. Is the actual change of y values, okay? Has a change to x plus delta x, okay? So what does this mean here, okay? Now, first of all, how do we actually get dy is equal to f prime of x dx? One thing about this is we know that dy dx is actually equal to f prime of x, okay? When we have y equal to f of x, right? When we take the derivative, okay? And then now, because dx is a non-zero real number, so in some sense, we could multiply both sides by dx. So now, we have dy equal to f prime of x dx, okay? Then, now let us look at what is the difference between dy versus the delta y now, okay? Then, now let us look at the diagram that we have, okay? In this case, again, the difference between x and x plus delta x is delta x here, okay? And then we denote by dx, okay? So, if, okay, maybe let us look at this, okay? If the function changing from x to delta x, x plus delta x, okay? Then in this case, the difference between, okay, the output f of x and f of x plus delta x, okay? The difference between this is what we call delta y. So delta y basically is the actual change from f of x to f of x plus delta x, okay? And to our example, okay? That means looking back to the example that we have, okay? This example right here is the one with the square root of 4.2, okay? Then in this case, that means, yeah. So in this case right here, then we actually have 4. And then of course the output that we have is actually, because it is a square root, right, of x. So then the output is actually 2. And then now to this one, if we have 4.2, then in this case, the output that we have is actually, it is a 2.049 390153, okay? So therefore, in this case right here, my delta y is actually, it will be 0.0493905153. Okay, so this is my delta y, is the actual change. Okay. On the other hand, what is dy now? Dy will be the approximate change. Okay. So in this case, again, this is my L of x. Okay. And then, of course, this point right here will be L of 4.5, 4.2. And then we know that L of 4.2 is equal to 2.05. Okay. Then now, in this case, that means, okay, this right here, it will be my dy. So dy is actually equal to 0.05, okay? Or if we work with the functions here, so I have dy is f prime of x dx, right? Okay, so then now we know that to this one, f prime of x is 1 over 2 times, or maybe I will say that here, it will be f prime of 4. F prime of 4 is 1 over 2 times square root of 4, or we get this one is 1/4. Okay. And then now we have dy, it will be f prime of 4 times dx. So then I will have 1/4 times, in this case, what is dx? Dx is 0.2, okay? Which is 1/4 times 1/5, but it's 1/20, which is 0.05, okay? This is exactly what we have here. So then, okay. So now you will see that just based on the example that we have here, we will be able to calculate the dy, which is easily then calculate the delta y, the actual change. Okay? So this is kind of like the idea why we develop this technique right here to work with differential then, okay? Because we would like to get the estimate, okay, of the change in the y directions then. Okay? Then now the key is, go back to the work now, right? The key is how do we find the dy, okay? Now the idea to this one, to find the dy, basically, it's just like what we did it here, okay? So we take the derivative, and then we multiply both sides by dx, just like this, okay? So to this one, then, let's see. I would like to take the derivative again, differential, we would like to find the differential, right? So we have dy dt, in this case, because we depend on t. And one thing about this is, okay, remember to this one, we have to use the chain rule. So e to the u, the derivative of e to the u is e to the u prime, right? So now we have this one is e to the tangent of pi t multiplied to the derivative of tangent of pi t. Okay. Then it will be e to the tangent of pi t. And then the derivative of tangent is secant square. So I will have secant square of pi t. And then we multiply to, again, the chain rule, pi t. Okay. So which is pi. So then the answer that I have, it will be pi secant square of pi t multiplied to e to the tangent of pi t. Okay. Okay, so this is how we take the derivative. But remember, we are not taking the derivative, we are looking for the differential. So the answer is dy equal to pi secant square pi t e to the tangent of pi t and then dt. Okay. Now we are going to work on b now. Okay. So we have y equal to square root of 1 plus natural log of z. Then first, I would like to rewrite this into 1 plus natural log of z raised to the power of 1/2. Okay. Then dy dz is equal to 1/2. 1 plus natural log of z raised to the power of negative 1/2. And we need to take the derivative of the inner functions. And it is 1 over 2 times square root of 1 plus natural log of z, and then multiply to the derivative of 1 is 0, but the derivative of natural log of z is 1 over z. Okay. So then I will have 1 over 2z square root of 1 plus natural log of z. Okay. And now dy is equal to dz over 2z square root of 1 plus natural log of z. Okay, so then this is my answer. Okay. Okay, so now let us look at the next example. I would like to find differential dy first and b evaluate dy for the given values x and dx. Okay. Okay. So then let's see. So I have y equal to 3 plus x squared raised to the power of 1/2. And dy dx is 1/2. 3 plus x squared raised to the power of negative 1/2. And then I take the derivative of the inner functions, which is 2x. Okay. And now 2 and 2 cancel. So I will have dy is x over square root of 3 plus x squared, okay, times dx. Okay. Okay, or sometimes we just write down x dx divided by square root of 3 plus x squared. Okay, so then now, this is A, and for B, we would like to evaluate dy. Evaluate at x equal to 1 and dx equal to negative 0.1, which is equal to 1 times negative 0.1 divided by square root of 3 plus 1 square. Okay. Then I have negative 0.1 divided by, this is square root of 4. Okay, so I have negative 0.1 divided by 2. And of course, in this case, I could write down as negative 0.05. Or if you want to, then you could multiply top and bottom by 10, make it become negative 1 over 20 then. Okay. Okay, so now then let us try to look at the next example now. So now I would like to use differential to estimate the amount of ping need to apply a coat of ping 0.05 cm thick to a hemispherical dome, okay, with diameter 50 meter. Okay. So then basically right now consider that we have a dome. Okay. So to this dome right here, the diameter is 50. So actually I need to use only the radius will be 25 meter then. Okay. Okay. And then now we would like to apply a coating, okay, all over the dome that we have. That mean right now I actually have the thickness, okay, of the coating. So maybe I call this, if I call the radius is R, okay, then the coating probably is the change in the R, which is the R then, right? Which is 0.05 centimeter. Okay. And now you will see that when we apply the pink to the dome, we increase the volume. So then now I would like to work with the volume. Okay. Okay. And now the volume of a sphere is 4 over 3 pi r cubed. But right now we only have half of it. So that means the volume that I have is only 2 over 3 pi r cubed. Then. And now the next thing that I would like to think of is, okay, so right now I actually to this unit right here, I have it in meter, and then I have it in centimeter. So what do I need to do is actually I need to, again, work with the same uh, unit. So one thing that we know is 1 meter is equal to 100 cm, centimeter, right? Okay. So now you have to decide if you want to work in centimeter or you want to work with meter then, okay? Okay, so maybe let us choose this one. Again, to me, maybe work with centimeter then. So then in this case, I have R equal to 25 meter, which is 2500 centimeter. And then my dr is 0.05 centimeter. Okay, so this is what we have. And then now I have V is equal to 2 over 3 pi r cubed. Okay. Then now I would like to find dV, okay, differential, okay. So it will be 2 over 3 pi. This is a constant. So I need to take the derivative of r to the power 3, which is 3r squared. And then I need to have dr. Okay. Okay, so then this is what I have then. Okay. And now I'm going to simplify this. Okay. So I will have dV is 2 pi r squared dr. Okay. And now I would like to evaluate dV when R equal to 2500 cm and dr is 0.05 cm. Okay. So I will have 2 pi 2500 square and 0.05. Okay. Then now I have 2 times 0.05, which is 0.1 pi. And then 2500 square is 625 with 40. And then we multiply to 0.1. So I will have 625,000 pi. Okay. And then to this one will be the unit, right? This one will have the cm square, and then this one will have the cm. So in this case, I will have cubic cm then. So the amount of pink used is about 625,000 cubic centimeter. Okay. Now remember this answer right here is the approximations, okay? If I want to actually work with the actual use, has been exact use, what I need to do, basically I need to find the volume. If I will add the R, it will be 2500 plus 0.05 minus the volume. If I will add 2500, then this will be the exact use, okay? Which is, again, we have to use a calculator to help us to do this thing. Okay, so then now let us look at our next example now, okay? So right now, suppose that the only information we have about the function f is we know that f of 1 equal to 5, and the graph of its derivative is shown. So now remember this graph is the derivative graph, not the actual function f, okay? So when what I would like to do is I would like to estimate, again, use the linear approximation to estimate f of 0.9 and f of 1.1, okay? Now remember, what we need to work it out is when we try to create the linear approximation L of x, okay? We need the slope of the tangent and we need a point, okay? So of course, in this case, I actually have a 0.15 already. Then what I need to do is I need to find what f prime of 1 equal to. If I know this, then I will be able to create the L of x, which is the linear approximations then, okay? Okay, so then let's see how do we actually work it out the problem, okay? So in this case right here, then let's see how do we actually find the L of x now, okay? So to this one, the slope of the tangent, which is equal to f prime of 1, okay? From the graph, we know that f prime of 1 is actually equal to 2, okay? So from this graph right here. And then we also have a 0.15, okay? So therefore, in this case right here, what we could do is we could using a y minus 5 equal to 2 times x minus 1, okay? And then now we have y equal to 2x minus 2 plus 5. So I have y equal to 2x plus 3. Okay. And then to this one, we are going to rewrite this, okay, into L of x is equal to 2x plus 3. Okay. And then now, let's see. Okay. Now, maybe let us try to go back to the problem to see why we could use the linear approximation so we could get to, again, get a better understanding about this problem, okay? So in this case, I have some functions, okay? This is the function f. And then right now, I actually have, again, the L of x is maybe at equal to 1, okay? This is my L of x is equal to 2x plus 3, okay? Is the linear approximation at x equal to 1, okay? Okay, then now, okay. And now I would like to use, again, I would like to evaluate, okay? Point 0.9, f of 0.9, okay? And also 1.1. Okay. And then now if you look at this graph right here, the function is actually is this f function, and then f of 0.9 is here. Okay. It is really close to L of 0.9, isn't it? And similarly to this one right here, okay, then f of 1.1 again is really close to L of 1.1. Okay, so this is the reason why we could use linear approximation to approximate. Okay, and now we're going to use L of x to estimate f of 0.9 and f of 1.1. Okay. So f of 0.9 is approximately equal to f of 0.9, which is equal to 2 times 0.9 plus 3. It is equal to 4.8. And f of 1.1 is approximately equal to L of 1.1. So it will be 2 times 1.1 plus 3, which is 5.2 then. Okay. Okay, so then this is actually how we use, again, differential to help us to work on some problem here then. Okay. Okay, so thank you.